Look up at the night sky on a perfectly clear evening. See those countless pinpricks of light, each one a distant sun, a galaxy, a swirling cosmic event. That view, as vast as it seems, is merely our backyard. It's everything we can possibly see, the observable universe, a bubble of reality centered right here on our little planet. But here's the thought that has captivated philosophers and scientists for centuries, a question that tickles at the very edge of our understanding: what lies beyond that bubble? If our universe has a horizon, a cosmic shore, what kind of ocean exists on the other side? It's a concept that feels almost forbidden, like trying to picture a color that doesn't exist. We are about to take a journey to that very edge, to peer over the cosmic fence into the great unknown. This isn't just about more stars or more galaxies. This is about confronting possibilities that challenge our fundamental notions of existence, reality, and our place within it all. This question, what lies beyond our universe, is more than just a scientific puzzle. It's a deeply human one. It's the ultimate expression of our curiosity, the same drive that pushed ancient explorers to map the edges of the world and modern astronauts to set foot on the moon. We are, by nature, a species that looks to the horizon and wonders what's on the other side. And in this video, we are going to take that instinct to its absolute extreme. We'll be exploring 25 of the most incredible, mind-bending theories that brilliant minds have proposed to answer this profound mystery. From the mathematically elegant to the philosophically startling, these ideas stretch the imagination in ways you might not think possible. We'll be venturing into realms where the laws of physics as we know them may break down, where other universes might bubble into existence, and where reality itself might be just one layer of a far grander cosmic structure. So get comfortable and open your mind, because we are about to dive into the deep end of cosmological thought. This journey is not about finding a single, definitive answer. The truth is, nobody knows for sure what lies beyond our cosmic horizon. Instead, it's an exploration of the most fascinating possibilities, a testament to human creativity and our relentless pursuit of knowledge. We'll unpack concepts that sound like science fiction, but are grounded in serious scientific and philosophical inquiry. It's going to be a fun, slightly wild ride to the frontier of what we can comprehend. By the end, you won't just have a list of ideas, you'll have a new perspective on the cosmos and our place within its magnificent and potentially infinite expanse. Let's begin. Our first stop on this journey into the unknown is perhaps the most staggering in its sheer scale, a concept born directly from the equations of modern cosmology. We begin with the level 1 multiverse. This idea doesn't require any new, exotic physics. Instead, it emerges naturally from a few simple assumptions that many cosmologists already accept. The first is that the universe is most likely infinite in size. The second is that matter, on the very largest scales, is distributed more or less uniformly. This is known as the cosmological principle, the idea that from any vantage point, the universe looks roughly the same, with no special center or edge. Now, if you combine an infinite universe with a finite number of ways to arrange the fundamental particles that make up reality, something remarkable happens. In an infinite space, every single possible configuration of matter must repeat. It's a simple matter of probability. Think of it like shuffling a deck of cards. With a finite deck, there are a vast but limited number of possible arrangements. If you had an infinite number of decks and you shuffled them for an infinite amount of time, you would eventually produce every possible sequence of cards, not just once, but an infinite number of times. Apply this logic to the cosmos. The region we can see, our observable universe, is like one specific, incredibly complex shuffle of the cosmic deck. All the stars, planets, and galaxies arranged in exactly the way we see them. But beyond the horizon of what our light can reach, the infinite expanse continues. Out there, in the endless cosmic ocean, you would eventually find regions where the shuffle of particles is almost identical to ours. A patch of space where everything is the same, except maybe one distant galaxy is rotated slightly differently. Further out, you'd find a region where a historical event on Earth unfolded with a minor change. And further still, you would encounter a region that is a perfect duplicate of our entire observable universe, complete with an identical Earth, an identical you, reading an identical sentence about this very theory. In fact, in a truly infinite universe, there isn't just one copy of you. There are an infinite number of copies, each living out every possible variation of your life. Every decision you didn't make, every chance encounter that never happened here, is a reality somewhere else. This isn't science fiction speculation. It's a direct consequence of the most straightforward interpretation of our cosmological models. The inflationary theory, which describes the universe expanding at an unimaginable rate right after the Big Bang, strongly suggests that space is flat and thus could very well be infinite. So, the level 1 multiverse isn't so much an extra hypothesis as it is an implication of what we might already believe. To visualize this, picture a vast, endless grid. Our entire observable universe, with its hundreds of billions of galaxies, is just one single cell in this infinite grid. We are forever trapped within our cell by the finite speed of light, but the grid itself stretches forever in all directions. It's a humbling thought. The entirety of our history, our triumphs, our sorrows, everything we consider unique and precious, is not just happening here, but is being echoed across infinity in countless variations. It suggests that the cosmos is not just vast, but truly saturated with every possible form of existence. But if the level 1 multiverse suggests our reality is just one tile in an infinite cosmic mosaic, then our next theory shatters that mosaic into an even more fragmented and diverse landscape. This idea, known as the level 2 multiverse or chaotic eternal inflation, takes us from a universe that's simply big to a cosmos that is actively and perpetually giving birth to new universes. The story begins not with the stars, but with the void itself. Right after the Big Bang, our universe underwent a period of incredibly rapid expansion called inflation, where space itself stretched faster than the speed of light. The leading theory, proposed by physicist Alan Guth, suggests that the engine behind this inflation was a peculiar type of energy inherent to empty space, known as false vacuum energy. Now, here's the crucial twist. According to the model of eternal inflation, this process never truly stops. While the false vacuum energy decayed in our region of space, settling down to form the stable universe we know, it's possible that on a much larger scale, the inflationary expansion continues forever. Picture a vast, bubbling cauldron of space-time expanding at an unimaginable rate. This is the inflating meta-universe or the multiverse background. Within this raging sea, quantum fluctuations cause tiny pockets of that false vacuum energy to randomly decay, like bubbles forming in a pot of boiling water. The moment a pocket decays, the inflationary expansion stops inside that bubble. But crucially, the space outside the bubble continues to inflate wildly, pushing these newborn bubbles far apart from one another. Each of these decaying pockets becomes its own separate Big Bang event, giving rise to an entirely self-contained universe, forever isolated from all the others. Our entire cosmos, with all its hundreds of billions of galaxies, would be just one of these countless bubbles adrift in an eternally inflating ocean. This isn't just one infinite universe with variations. This is an infinite number of separate universes, each with its own unique birth and potentially its own unique set of physical laws. This is where the theory becomes truly profound, because it offers a potential answer to one of the deepest mysteries in physics, the fine-tuning problem. The fundamental constants of our universe, the strength of gravity, the mass of an electron, the force that holds atomic nuclei together, seem perfectly calibrated to allow for the existence of stars, planets, and ultimately life. If any of these values were even slightly different, atoms wouldn't form, stars wouldn't shine, and the cosmos would be a dark, sterile void. So why is our universe so hospitable? Eternal inflation provides a compelling, if humbling, explanation. In the endless froth of the multiverse, every possible set of physical constants will be realized in some bubble universe. The vast majority of these universes would be stillborn or chaotic, utterly incapable of supporting any complex structures, but in a rare few, purely by chance, the numbers line up just right. We don't live in a special universe, we simply live in one of the few where the conditions allowed for our existence. It's like winning a cosmic lottery, but with an infinite number of tickets being drawn, a winner was inevitable. While the bubble universes of eternal inflation exist in a vast sea of inflating space, our next theory proposes that the multiverse is not somewhere far away, but is being generated right here, right now, with every passing moment. This is the Level 3 multiverse, born not from cosmology but from the bizarre and counterintuitive world of quantum mechanics. At the heart of this idea is a puzzle that has stumped physicists for a century: the strange behavior of particles at the smallest scales. In our everyday world, things seem definite. A ball is either here or there. But in the quantum realm, particles exist in a blurry state of potential called a superposition, where they can be in multiple places or states at once, only settling into a single, definite reality when we observe or measure them. This transition from fuzzy potential to concrete fact is known as the collapse of the wave function, and it has always been a deeply mysterious process. Why does observation make reality snap into focus? In 1957, a young physicist named Hugh Everett offered a radical solution. He proposed that the wave function never actually collapses. Instead, every single possible outcome encoded within a quantum superposition actually happens. The moment a quantum event occurs with multiple possible outcomes, the entire universe splits, branching off into multiple, equally real timelines. In one branch, the particle goes left, in another, it goes right, and both of these new universes are completely separate and real. This is the many worlds interpretation. It means that at this very second, for every quantum event, every flicker of an electron, every random decay of an atom, new universes are budding off from our own. But it goes far deeper than just particles. If every quantum possibility becomes reality, then every event that depends on quantum mechanics, which is essentially every event, also branches. Think about a simple choice, like deciding to turn left or right while walking down a street. Your decision is ultimately a process driven by electrical signals in your brain, which are themselves the result of countless quantum events. In the many worlds view, there isn't just one outcome where you, after a brief moment of indecision, choose to turn left. There is another, fully real universe where an identical version of you, up until that exact split second, turns right instead. In that other reality, the rest of their day, and indeed the rest of history, unfolds differently from that point forward. This branching happens for every trivial event, every chance occurrence, every single possible alternative. There is a universe where you caught that bus you just missed. There is a universe where a different sperm fertilized the egg that became you. There is a universe where the dinosaurs never went extinct. The branching is constant and infinite, creating a mind-bogglingly vast tree of all possible realities, a multiverse of alternate histories and futures. This has profound and perhaps unsettling implications for our sense of self and free will. In this view, there is no single you. Instead, you are a constantly branching entity. Every version of you in every possible timeline is equally real. The you reading this sentence is just one thread in an infinite tapestry of selves. It challenges the very idea of a single, linear life story. Instead of a path not taken, every path is taken by some version of you. This doesn't necessarily negate free will. Your conscious mind still makes choices. It's just that all other possible choices are also made by your other selves in their respective branches. The many worlds interpretation is arguably the most democratic theory of reality ever conceived, granting actual existence to every possibility, no matter how improbable. It suggests that beyond the solid world we perceive lies a shimmering, fractal-like structure of limitless potential, where all stories are true. If the many worlds interpretation suggests that reality is a tree endlessly branching with every quantum possibility, then our next theory proposes something even more fundamental and abstract. This is the Level 4 multiverse, also known as the mathematical universe hypothesis, championed by physicist Max Tegmark. It pushes the boundaries of what we even mean by reality. Tegmark's starting point is a simple yet staggering observation. Our physical universe appears to be perfectly described by mathematics. The orbits of planets, the behavior of light, the interactions of subatomic particles, all of it can be captured with breathtaking precision by mathematical equations. This uncanny effectiveness of mathematics in the natural sciences has long been a source of wonder. Tegmark takes this idea to its ultimate logical extreme. He proposes that this isn't a coincidence because the universe is mathematics. More specifically, our physical reality is not just described by a mathematical structure, it is that mathematical structure. What does this actually mean? Think about something simple and abstract like a circle. A circle has certain properties. It's a set of points equidistant from a center. This definition exists independently of anyone thinking about it. You don't need a physical drawing of a circle for the mathematical concept of a circle to be true. Tegmark suggests that our universe works the same way. The equations of general relativity and quantum field theory that govern our cosmos define a specific, incredibly complex mathematical structure. And according to this hypothesis, that structure is our universe. But here's the truly radical part. If our universe is one mathematical structure, then why should it be the only one? There are infinitely many possible mathematical structures, some simple, like the geometry of a four-dimensional cube, and others fantastically complex, governed by rules and dimensions we can scarcely conceive. The mathematical universe hypothesis posits that every single one of these mathematically consistent structures exists as a physical reality. There is no distinction between the abstract world of mathematics and the concrete world of physical existence. This leads to a multiverse of literally unimaginable diversity. The Level 1 multiverse gave us more stars and galaxies. The Level 2 gave us bubble universes with different physical constants. The Level 3 gave us branching timelines, but the Level 4 multiverse is something else entirely. Beyond our cosmic horizon lies not just other universes with slightly stronger gravity or more dimensions of space, but universes built on entirely different foundational laws. Some might be static and timeless, containing nothing but intricate, frozen geometric patterns. Others might be buzzing with chaotic, fleeting forms of existence that pop in and out of being according to rules that have no analog in our physics. There could be universes where the concept of time as a one-way arrow doesn't exist, or where the number of spatial dimensions is 100 or just 1. The only constraint is that the structure must be mathematically consistent. It cannot contain logical contradictions. Within this infinite library of all possible mathematical structures, our universe is simply one particular volume. The one whose equations happen to allow for the emergence of stars, planets, and self-aware consciousness like us. This idea has deep philosophical implications that challenge our most basic intuitions. It suggests that the quest for a theory of everything, a single set of equations that perfectly describes our universe, might be missing the point. The point isn't to find the equations that built our universe, because an infinite number of other equation sets have built other universes. Instead, the real question becomes, why do we find ourselves in this particular mathematical structure? The answer, often called the anthropic principle, is that we could not find ourselves in a universe incapable of supporting our existence. We are a part of the mathematical structure we inhabit, so we naturally observe the laws that allowed us to arise. A universe governed by chaotic or sterile mathematics would have no one to ask these questions. This theory elegantly dissolves the fine-tuning problem. The constants aren't tuned at all. In the vast landscape of all mathematics, a small subset will inevitably be complex enough to contain observers. We are simply living proof that our particular mathematical structure belongs to that subset. It's a humbling perspective that places mathematics, not matter, as the true fundamental substance of reality. Yet, even as we grapple with the idea that all mathematically possible worlds are equally real, another theory proposes that our own world is not at all what it seems. This is the holographic universe principle, a concept so profound that it suggests the three-dimensional reality we experience. The depth of space, the solidity of matter, is nothing more than a magnificent illusion. Imagine watching a breathtakingly realistic movie on an IMAX screen. You feel immersed in a vast three-dimensional world, but you know that all the information creating that illusion is actually encoded on a flat, two-dimensional surface, the movie screen itself. The holographic principle applies this same logic to the entire cosmos. It proposes that our universe, with all its galaxies, stars, and planets, is a projection. The true, fundamental reality is a two-dimensional surface that encodes all the information needed to generate our three-dimensional experience. According to this idea, what lies beyond our universe is not more space in the conventional sense, but this lower dimensional boundary, the cosmic equivalent of the projector's film. The origins of this mind-bending idea come from an unexpected place, the study of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, a measure of the disorder or information content within a system, is proportional not to its volume as one might expect, but to the surface area of its event horizon. This was a revolutionary insight. In everyday life, the amount of information you can cram into a box depends on its volume. But Bekenstein's work, later refined by Stephen Hawking, suggested that the maximum amount of information that can be stored in any region of space is determined by the area of its boundary, not the volume it contains. It's as if all the information about everything that falls into a black hole gets smeared out and stored on its surface like a cosmic hard drive. Our universe, when considered as a whole, also has a boundary, the cosmological horizon, the ultimate edge of our observable bubble. The holographic principle extends the black hole logic to the entire cosmos, suggesting that all the information about every particle, every force, and every event happening within our universe is encoded on this distant two-dimensional surface. This leads to a truly staggering implication. If the information that makes up your body, your memories, and the world around you is actually stored on a flat surface at the edge of the universe, then your rich, three-dimensional life is a kind of decoding or projection of that data. You are, in a very real sense, a hologram. This isn't just a poetic metaphor, it's a serious proposal within string theory and quantum gravity. The mathematics suggests that the fundamental building blocks of reality are not point-like particles dancing in a three-dimensional arena, but tiny, one-dimensional strings whose vibrations create all the forces and particles we know. In certain formulations of string theory, the description of these strings and their interactions is mathematically equivalent to a theory that operates on a lower dimensional boundary. This duality means that a complex gravitational theory in three dimensions can be perfectly translated into a simpler quantum theory in two dimensions without any loss of information. The three-dimensional world, complete with gravity, emerges from the two-dimensional one. One of the most powerful aspects of this theory is its potential to solve the greatest problem in modern physics, unifying Einstein's theory of general relativity which describes gravity, and the large-scale universe with quantum mechanics, which describes the world of the very small. These two pillars of physics are mathematically incompatible. The holographic principle offers an elegant way out by suggesting that gravity itself is not a fundamental force but an emergent phenomenon, something that arises from the complex interactions of information on the lower dimensional boundary. It provides a framework where the two theories can coexist. Gravity, in this view, is a consequence of the holographic projection, much like the illusion of depth in a 3D movie is a consequence of the data on a 2D screen. What we perceive as the fabric of spacetime might be a secondary effect, a collective outcome of countless bits of information interacting on the cosmic horizon. This completely reframes our search for a theory of everything. The fundamental laws of reality might not be laws of physics as we know them, but laws of information processing. Contemplating the holographic universe can feel deeply disorienting. The solid ground beneath your feet, the vast emptiness of space, the very notion of distance, all of it becomes a sophisticated illusion rendered for our benefit. It suggests that reality is far more abstract and informational than material. But if our universe is a projection, a cosmic simulation of sorts, then who or what is the projector? This question leads us directly to our next theory, one that has captured the public imagination like no other. While many theories we've explored stretch the concept of reality into parallel or projected forms, the cyclic model offers a profoundly different vision, one of cosmic rhythm. Instead of a single, linear story beginning with a mysterious Big Bang and ending in cold, empty darkness, this theory suggests our universe is engaged in an eternal dance of death and rebirth. It proposes that the cosmos has no true beginning and no final end. What lies beyond the ultimate fate of our universe is not an alien landscape or a higher dimension, but simply the fresh start of the next cosmic cycle. Our universe, in this view, might be just one heartbeat in the infinite life of a timeless entity. The classic version of this idea is often called the Big Bounce. Imagine the entire history of our universe, from the Big Bang to the present day and into the far, far future. Current observations suggest we live in a universe that is expanding at an accelerating rate, likely leading to a cold, thin, and dark finale known as the heat death. But the cyclic model asks, what happens after that? It posits that after an unimaginably long period, the force of dark energy that is driving the expansion could weaken, or the collective gravitational pull of all the matter and dark matter in the universe could finally take over. Gradually, the expansion would slow, halt, and then reverse. The universe would begin to contract, galaxies would rush together, temperatures would soar, and all of space would collapse back toward a single, incredibly hot and dense point, a state very similar to the one from which our Big Bang emerged. But instead of being a definitive end, this big crunch would act as a cosmic reset button. The immense energy and density would trigger a new Big Bang, and a new universe would be born from the ashes of the old one. This cycle of expansion and contraction could, in principle, repeat forever. This idea elegantly sidesteps one of the most persistent philosophical puzzles of cosmology: what caused the Big Bang? If the Big Bang was the absolute beginning of time and space, then the question, what happened before, is meaningless as time itself did not exist. This is a difficult concept to grasp. The cyclic model offers a more intuitive, though no less spectacular, answer. There was no ultimate beginning, there was always a before. Our Big Bang was not the start of everything, it was merely the most recent turning point in an endless cycle. The universe is like a phoenix, perpetually dying in a fiery collapse only to be reborn again, each cycle potentially lasting trillions of years. What lies beyond our universe's end is not a void, but the next chapter in an infinite story. Modern physics has given this ancient idea a sophisticated update, most notably in the form of the ekpyrotic universe scenario, which emerges from string theory. The word ekpyrotic comes from the Greek for conflagration or out of fire, and the theory replaces the Big Crunch with an equally dramatic event. It proposes that our three-dimensional universe is actually a membrane, or brane for short, existing within a higher dimensional space called the bulk. We are stuck on our brane and cannot perceive these extra dimensions, but other branes could be floating nearby in this grander arena. The ekpyrotic model suggests that the Big Bang was not an explosion from a singularity, but was caused by a collision between our brane and a neighboring one. Think of two sheets of paper floating parallel to each other in a vast, empty room. If they gently collide, the impact would release an enormous amount of energy, which from our perspective confined to the paper would look like a sudden, hot, dense beginning, a Big Bang. In this cyclic brane world, the entire cosmic story unfolds differently. After the collision, the two branes bounce apart, initiating a period of expansion and cooling that becomes our universe. Eventually, the branes, drawn together by a force across the higher dimensions, begin to approach each other again. This sets the stage for the next collision, the next Big Bang, and the next universe. This model solves several thorny problems with the original Big Bang theory, such as why the early universe was so uniform. The slow, gentle approach of the branes before the collision has a smoothing effect, naturally explaining the large-scale consistency we observe. It paints a picture of a cosmos where the ultimate fate is not silence, but another encounter. What lies beyond our universe is not empty space, but the approach of a cosmic sibling, destined to meet us again and spark a new creation. This vision of the cosmos is one of eternal recurrence, a grand, rhythmic pulse across the dimensions that has no need for a definitive start or a lonely end. But if the cyclic model offers a vision of cosmic rebirth through dramatic collisions, the theory that gives this idea its most sophisticated form also opens up an even vaster and more exotic possibility. This brings us to the brane multiverse, a concept that arises from the depths of string theory. To understand this, we need to shift our perspective on the very nature of space itself. We are all familiar with the three dimensions of space: length, width, and height, and the one dimension of time. But string theory, a leading candidate for a theory of everything, proposes that this is not the full picture. It suggests that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. And for the mathematics of string theory to work coherently, these strings must vibrate in a space-time that has not 3, but 10 or 11 dimensions. So where are these extra dimensions? The theory posits they are compactified, curled up into sizes so fantastically small that they are completely hidden from our perception, like the circumference of a garden hose that looks like a simple line from a great distance. This is where branes enter the story. The word brane is derived from membrane, and it refers to a multidimensional object that can exist within this higher dimensional space, which string theorists call the bulk. A brane can have any number of dimensions. A zero brane is a point, a one brane is a string, a two brane is a membrane like a sheet, and so on. Our entire universe, according to this idea, could be a three brane. That means that everything we know, every galaxy, every star, every one of us, is stuck to this three-dimensional surface. The three spatial dimensions we experience are the vast expanse of the brane itself, while the other dimensions are part of the higher dimensional bulk that surrounds us. We are like characters living on the surface of an immense, multidimensional soap bubble, completely unaware of the greater space in which our bubble floats. This leads to a staggering implication for what lies beyond our universe. What's out there is not more empty space like our own, but this higher dimensional bulk. And within this bulk, our brane is not alone. There could be a countless number of other branes, each one its own separate universe, floating in the bulk like slices of bread in a cosmic loaf. These other branes could be mere microscopic distances away from us in these extra, compactified dimensions, yet entirely separate because all the forces and particles of our universe are confined to our brane. The only force thought to be able to leak across the bulk is gravity. This could explain why gravity is so phenomenally weak compared to the other fundamental forces. Its strength is diluted as it spreads out into the full volume of the higher dimensional bulk. The diversity of this brane multiverse is almost beyond comprehension. Each of these branes could have a different number of dimensions, different vibrational patterns of its strings, and therefore different fundamental laws of physics. Some might be barren, containing only a featureless energy field. Others might be bursting with complex structures and life forms based on entirely different principles. This connects to the idea of the string theory landscape, a metaphorical way of describing the mind-boggling number of possible stable configurations or vacuum states that the equations of string theory allow. The number is estimated to be around 10 to the power of 500. That's a 1 followed by 500 zeros, a figure so large it dwarfs the number of atoms in our observable universe. Each of these possible configurations corresponds to a universe with a unique set of physical constants, particles, and forces. In the brane multiverse, this vast landscape is not just a theoretical possibility. It is an actual reality, with each possible universe existing on its own brane. This framework provides a powerful and elegant explanation for the very origin of our universe, the Big Bang. As mentioned in the cyclic model, one compelling scenario is that our Big Bang was triggered by a collision between our brane and a neighboring one. The immense energy released in such a cosmic impact would have heated our brane to an incredible temperature, creating the hot, dense state we identify as the beginning of our cosmic timeline. These collisions might not be rare, one-off events, but part of a perpetual cycle, with branes oscillating in the bulk, colliding and moving apart in eternal rhythm. What lies beyond our universe, then, is not a static emptiness, but a dynamic, higher-dimensional arena where other universes coexist, and where the very event that gave birth to our reality might be a common occurrence. It suggests that our cosmic home is not an isolated island, but one participant in a grand, multidimensional ballet. But if the brane multiverse suggests we live on a membrane floating in a higher dimensional space, our next theory asks an even more direct and personal question about the nature of our existence. This is the simulation hypothesis, the provocative idea that our entire universe, with all its galaxies, stars, and conscious beings, is not a fundamental reality at all, but an incredibly sophisticated computer simulation, much like a video game created by a civilization with technology far beyond our own. In this view, what lies beyond our universe is not a void or another dimension, but the physical hardware of the supercomputer that's running our reality, the base, or real, universe where our creators reside. The argument for this idea often starts with a simple extrapolation of technological progress. Think about the video games of just a few decades ago, simple, blocky pixels moving on a screen. Now consider the trajectory of virtual reality and computing power. We are already creating immersive digital worlds that can fool our senses. If our civilization continues to advance for thousands or millions of years, is it not plausible, perhaps even inevitable, that we would develop the capability to create simulations so perfect that the conscious beings within them would be completely unaware they are living in a constructed reality? Now take that logic one step further. If one advanced civilization can create such simulations, and if it's possible to create not just one but many, perhaps billions, of these simulated universes, then a simple statistical argument emerges. The number of simulated minds would quickly and vastly outnumber the number of minds in the original, base reality. Therefore, if you were a conscious being, the odds are overwhelmingly high that you are not in the original reality, but in one of the countless simulations. This line of reasoning is supported by some peculiar features of our own universe that seem almost programmed. The fact that reality appears to be quantized, broken down into discrete, indivisible units like pixels on a screen, is a key piece of evidence for some proponents. In our world, energy, space, and time all have fundamental minimum units, a Planck length and a Planck time, below which the concepts of distance and duration break down. This could be interpreted as the resolution limit of the simulation, the point where you start to see the pixelation of the cosmic code. Furthermore, the universe's deeply mathematical nature, which we discussed with the mathematical universe hypothesis, could be seen not as evidence that the universe is math, but that it was built on mathematical rules, just like a computer game is built on its source code. The laws of physics would be the algorithms that the simulation runs on, and the constants of nature would be the hard-coded parameters set by the programmers. The philosophical implications of this idea are profound and often unsettling. If we are in a simulation, it redefines concepts like free will, purpose, and the soul. Are our choices truly our own, or are they the result of deterministic code? Is there a higher purpose, or are we merely entertainment, a science project, or even someone's forgotten server farm, running in the background of a much grander reality? This theory also introduces the terrifying possibility of nested simulations. If an advanced civilization can create a simulated universe containing conscious beings, what's to stop those simulated beings from eventually developing their own technology and creating simulations within their simulation? This could lead to an infinite regress of realities within realities, a cosmic Russian nesting doll where no one knows which layer is truly the original. Our creators might themselves be simulations created by another, even more advanced civilization. This vertiginous thought challenges the very notion of what is real. Unlike many of the theories we've explored, the simulation hypothesis is unique in that it is, in principle, falsifiable. Scientists have proposed ways we might look for glitches in the matrix anomalies that could betray the underlying computational nature of our world. These might include finding inconsistencies in the fundamental constants, observing patterns in cosmic background radiation that resemble error-correcting code, or discovering that the laws of physics have a built-in optimization that resembles a computational shortcut. Finding such evidence would be the most dramatic discovery in human history, fundamentally altering our understanding of existence. But even in the absence of proof, the hypothesis serves as a powerful modern mythology, a lens through which we can question the nature of our reality in an age defined by information technology. It suggests that the ultimate frontier might not be in the distant stars, but in the very code of existence we take for granted. If our universe is a sophisticated simulation, then the reality we perceive is fundamentally a construct of information. But what if the cosmos is structured in a way that is both real and yet infinitely layered in a manner that challenges our understanding of scale? This brings us to one of the most visually compelling ideas on our list: black hole cosmology. This theory proposes a breathtakingly elegant and perhaps terrifying connection between the largest and smallest structures in existence. It suggests that our entire universe, in all its vastness, is not expanding into some abstract nothingness, but is actually contained within the interior of a black hole belonging to a much larger parent universe. And by extension, every single black hole that forms within our cosmos could be the seed for a brand new, separate universe of its own. To grasp this, we need to reconsider what a black hole really is. We typically think of it as a cosmic vacuum cleaner, a point of infinite density from which nothing, not even light, can escape. But the mathematics describing the interior of a black hole, particularly a rotating one described by the Kerr solution, reveals something far more interesting than a simple dead end. Inside, the roles of space and time can become twisted, and the point of infinite density, the singularity, might not be a point at all, but a bridge to another region of spacetime. This is the concept of an Einstein-Rosen bridge, more popularly known as a wormhole. Now, instead of imagining the wormhole as a tunnel connecting two distant points in our universe, black hole cosmology proposes that the other end of the wormhole isn't just another location, but an entirely new space-time continuum that begins its own expansion. The Big Bang, in this view, was the violent birth of this new space-time on the other side of the singularity. The evidence for this is more than just speculative geometry. Consider the fundamental properties of our universe and compare them to the theoretical properties of a black hole. A black hole is defined by its event horizon, a one-way boundary. Our universe also has a cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. We are forever trapped inside our observable bubble, just as an object is trapped inside a black hole. Furthermore, the entropy of a black hole, as we discussed with the holographic principle, is proportional to the area of its event horizon. Our universe, too, has a surprisingly low total entropy when you consider its horizon area, a fact that some physicists argue is exactly what you would expect if our cosmos were a black hole-like object. The equations start to look eerily similar, suggesting that the universe we inhabit might share a deep, fundamental identity with the most enigmatic objects within it. This leads to a truly fractal vision of reality. If our universe was born from a black hole in a parent universe, then it stands to reason that the stellar mass and supermassive black holes we observe in our own cosmos formed from the collapse of massive stars or at the centers of galaxies could each be the genesis points for their own daughter universes. Within one of those universes, the same process would repeat. This creates a cosmic family tree, an infinite nesting doll of universes, each contained within the black hole of its predecessor. What lies beyond the ultimate edge of our observable universe, beyond our cosmic horizon? According to this theory, it's not empty space. It is the interior of the immense black hole in the parent universe that gave birth to us. We are on the inside looking out, but the out is a realm with different laws of physics, a different flow of time, and perhaps entirely different forms of matter and energy that we can never directly perceive or interact with. This idea offers a radical, and some would say poetic, solution to the mystery of the Big Bang's origin. Instead of a singularity appearing from nothing, the Big Bang was the result of a pre-existing astrophysical process in a higher-order reality. It provides a mechanism for the continuous creation of new universes, a form of cosmic reproduction. Our entire cosmic history, from the first instant of inflation to the formation of galaxies and the evolution of life, is all happening within the confined space of an object that is, from an external perspective, just one of countless black holes in a grander cosmos. This theory seamlessly connects the terrifyingly small scale of a gravitational singularity with the impossibly large scale of the expanding cosmos, suggesting that the key to understanding the whole universe might be hidden in the mysterious hearts of its darkest objects. While the idea of a universe endlessly reborn through dramatic collisions or cosmic bounces is captivating, one of the most brilliant minds of our time has proposed a cycle of such profound elegance that it redefines the very meaning of death and birth. This is Sir Roger Penrose's conformal cyclic cosmology, a theory that suggests the ultimate fate of our universe is not a finale, but a quiet, seamless transformation into the next. Penrose's vision dispenses with the need for a fiery big crunch or a brane collision. Instead, he proposes that the universe achieves immortality through a process of gentle mathematical equivalence, where the end of time in one era becomes the beginning of time in the next. To understand this, we must first confront the most likely destiny for our cosmos based on current observations, the heat death. Trillions upon trillions of years from now, the universe will have expanded to an extraordinary degree. All stars will have long since burned out, their fuel exhausted. Black holes, once thought to be eternal, will have slowly evaporated away due to Hawking radiation. The cosmos will be an incredibly vast, cold, and dark emptiness, populated only by a thin, uniform haze of fundamental particles and radiation, spread so thin that interactions become vanishingly rare. It is a state of maximum entropy, a thermodynamic equilibrium where no work can be done, no structure can form, and effectively, no time can be felt. It appears to be the ultimate silent end, but Penrose asks a revolutionary question. What if this bleak, featureless state doesn't look like an end to the laws of physics? What if, when you strip away all the scales of measurement, it looks exactly like a beginning? This is where the complex but beautiful idea of conformal rescaling comes in. Imagine you have a detailed map of the entire world. The map has a scale. 1 inch might represent 100 miles. Now, imagine you could change that scale in a very specific way. You could make the map so large that the entire continent of Asia fits on the head of a pin, or so small that a single grain of sand is mapped to the size of a football field. In this process of extreme rescaling, you lose all sense of absolute distance. A mountain and a molehill become indistinguishable in size because the concept of bigness and smallness has been erased. However, something crucial is preserved: the angles between things. The geometric relationships, the shapes, remain intact. This preservation of angles, not distances, is the essence of conformal geometry. Penrose applies this concept not just to space, but to the entire fabric of space-time. In the far, far future, at the end of time in our universe, the cosmos is effectively empty and devoid of any meaningful scale. There are no clocks to measure time because all processes have stopped. There are no rulers to measure space because all distinct structures have dissolved. In this state, the concepts of long and short, or fast and slow, become meaningless. The universe has no defining feature left except its conformal geometry, the fundamental angles and relationships of its empty spacetime. And here is the breathtaking leap. Penrose realized that this infinite, cold, low-energy emptiness is mathematically identical through a conformal rescaling to the ultra-hot, ultra-dense, low-entropy singularity of the Big Bang. The end of one cosmic cycle, or eon as he calls it, is conformally equivalent to the beginning of the next. To visualize this, don't think of a timeline that ends and then starts again with a bang. Think of it as a circle, but a very peculiar one. At the top of the circle is the hot, dense Big Bang of our eon. The circle then expands outward, tracing the entire history of our universe, the formation of galaxies, the evolution of life, the eventual heat, death, all along the circumference. As we follow the circle around, the universe becomes larger, colder, and emptier. Now, here is the profound twist. When we reach the very bottom of the circle, the point of maximum expansion and emptiness, that point is not a dead end. Through the magic of conformal rescaling, that point is the same point as the Big Bang at the top of the circle for the next eon. The infinite future of our universe is, in a conformal sense, the 0 point of the next. The transition is seamless. There is no boundary, no moment of creation, just a smooth mathematical transformation where the end becomes the beginning. This theory even offers a potential way to find evidence for these previous eons. Penrose suggests that the violent events at the end of the prior eon, such as the evaporation of supermassive black holes, could have left faint imprints on the next Big Bang in the form of concentric circles of subtle temperature variation in the cosmic microwave background radiation. While the search for these Hawking points is ongoing and controversial, it represents a stunning possibility that we might one day peer not just beyond our observable universe, but beyond the very beginning of our own cosmic timeline, into the graveyard of a universe that came before ours. It's a theory that grants the cosmos a form of eternal life, not through violent rebirth, but through a quiet, graceful, and infinite metamorphosis. While many of the theories we've explored involve dynamic processes and dramatic transformations, Our next stop on this journey takes us back to a simpler, more serene vision of the cosmos, one that was once championed by the greatest scientific mind of the 20th century. This is the idea of the static universe, a model that proposes the cosmos is fundamentally unchanging, infinite in both space and time. In this view, there is no beyond in a temporal sense because the universe has always existed and will always exist exactly as it is. The question of what came before the Big Bang or what lies past the cosmic horizon becomes meaningless. The universe is the ultimate, eternal backdrop against which all stories are told. This concept was deeply appealing to the scientific sensibilities of the early 1900s, including those of Albert Einstein himself. When he published his theory of general relativity in 1915, the equations described a dynamic universe, one that should either be expanding or contracting. This notion of a cosmos with a beginning and an end was so philosophically unsettling to Einstein, who, like many of his contemporaries, believed in an eternal and steady-state universe, that he introduced a fudge factor into his own equations. He called it the cosmological constant, a term represented by the Greek letter lambda. This constant represented a repulsive force, a kind of anti-gravity that would perfectly balance the attractive force of all the matter in the universe, preventing it from collapsing under its own weight and resulting in the static, unchanging cosmos he expected. For a time, this model of an infinite, eternal, and stable universe held sway. However, this elegant, static vision of reality was shattered in the late 1920s by the groundbreaking observations of astronomer Edwin Hubble. By meticulously studying the light from distant galaxies, Hubble made a startling discovery. Nearly every galaxy was moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static at all, it was expanding. This was the definitive evidence that the cosmos had a history, a starting point from which everything began what we now call the Big Bang. Upon learning of Hubble's results, Einstein reportedly called his introduction of the cosmological constant the biggest blunder of his career. He had allowed his philosophical preference for a steady state to override what his own equations were clearly telling him: the universe was dynamic. The static universe model was abandoned, and cosmology embarked on a new path focused on understanding the evolution of the cosmos from a hot, dense beginning. But the story of the cosmological constant doesn't end there. In one of the most remarkable reversals in the history of science, lambda has made a spectacular comeback. In the late 1990s, astronomers studying distant supernova made a discovery as shocking as Hubble's. They found that the expansion of the universe is not slowing down, as everyone had assumed due to the pull of gravity, but is actually accelerating. Something is pushing the galaxies apart at an ever-increasing rate. This mysterious something was dubbed dark energy, and the leading candidate for what dark energy could be. None other than Einstein's cosmological constant. The repulsive force he invented to hold the universe steady now appears to be the very force that is driving it apart at an accelerating pace. The biggest blunder, it turns out, might have been one of his greatest insights after all, even if for the wrong reason. This gives the static universe theory a fascinating, if ironic, legacy. While the idea of a completely unchanging cosmos is definitively ruled out by the evidence for the Big Bang and cosmic expansion, dark energy introduces a different kind of permanence. If dark energy continues to dominate, the far future of the universe looks less like a dramatic collapse and more like an eternal, ever-thinning, and increasingly empty state, a cold, dark, and quiet version of infinity. In this light, the static universe model serves as a crucial historical contrast. It reminds us of the power of preconceived notions and the importance of following the evidence, even when it leads to uncomfortable conclusions. It also highlights the incredible capacity of science to correct itself, showing how a discarded idea can be resurrected in a completely new context to help solve one of the greatest mysteries of our time. Now, as we move from the grand cosmic cycles and multidimensional membranes of mainstream cosmology, we encounter a theory that proposes a fundamentally different engine for the universe itself. This is the plasma universe, also known as the electric universe hypothesis. It's a perspective that challenges gravity's throne as the primary sculptor of the cosmos, arguing instead that we live in an electrically active, plasma-filled universe where electromagnetic forces are the true architects of the large-scale structures we see. In this view, the cosmos is not dominated by the silent, relentless pull of gravity, but by the dynamic, filamentary flow of electric currents across the vastness of space. And if this is true, then what lies beyond our observable horizon is not a mystery of dark matter or dark energy, but simply more of this infinite, eternally evolving electrical tapestry. To understand this idea, we first need to appreciate the fourth state of matter, plasma. While solids, liquids, and gases are familiar here on Earth, plasma is by far the most common state of matter in the visible universe, making up over 99% of all luminous material. Stars, for instance, are colossal balls of hot plasma. Plasma is essentially an ionized gas, a soup of positively charged atoms and negatively charged free electrons. Because its particles are charged, plasma is an excellent conductor of electricity and is highly responsive to electromagnetic fields. Crucially, when electric currents flow through plasma, they don't travel in a simple, straight line. Instead, they tend to pinch and twist into long, thin, filamentary structures. These are known as Birkeland currents, named after the Norwegian explorer Christian Birkeland, who first proposed in the early 20th century that the auroras borealis were caused by charged particles from the sun flowing along the Earth's magnetic field lines. Proponents of the plasma universe take this local phenomenon and scale it up to a cosmic level. They suggest that the same fundamental processes that create the beautiful, shimmering curtains of the auroras in our sky are also responsible for forming galaxies, stars, and even shaping planetary nebulae. In this model, vast, galaxy-spanning Birkeland currents flow through the intergalactic medium, immense rivers of electricity that weave through the cosmos. Where two or more of these cosmic currents flow close together, their magnetic fields cause them to attract and spiral around each other. This pinching effect, they argue, is what gathers the primordial plasma and dust to form spinning galactic disks, complete with their characteristic spiral arms. Rather than gravity slowly pulling gas clouds together over billions of years, the electric universe posits that galaxies can form relatively quickly through the organized, sculpting force of electromagnetism. This would mean the beautiful spiral galaxy we call home, the Milky Way, might not be an island in a gravitational sea, but a node in a cosmic circuit of unimaginable scale. This alternative framework also offers its own explanations for two of the pillars of modern cosmology: the redshift of distant galaxies and the cosmic microwave background radiation. In the standard Big Bang model, the redshift of light from galaxies, where their light is shifted toward the red end of the spectrum, is interpreted as a Doppler effect, evidence that those galaxies are moving away from us due to the expansion of the universe. The electric universe proposes a different cause. That light can lose energy and thus redshift as it travels through a tenuous, but not entirely empty, intergalactic plasma over these immense distances. This tired light hypothesis, if true, would mean the universe is not expanding at all, and therefore has no need for a Big Bang beginning. Similarly, the cosmic microwave background, which mainstream science sees as the cooled remnant radiation from the hot, dense early universe, is interpreted by electric universe proponents as the simple thermal emission from all the warm, dusty plasma that fills the space between stars and galaxies, the steady-state glow of an eternal, infinite cosmos. While the plasma universe has a dedicated following and offers visually compelling explanations for many cosmic phenomena, it is important to note that it remains a fringe theory within the astrophysics community. Mainstream cosmology points to a vast body of evidence that is difficult to reconcile with a purely electric model, such as the precise blackbody spectrum of the cosmic microwave background and the observed abundance of light elements which strongly support the Big Bang narrative. Yet, the enduring appeal of the electric universe lies in its power to challenge established dogma and to remind us that our understanding of the cosmos is always a work in progress. It presents a vision of a living, electrically connected universe, a far cry from the cold, gravity-dominated void of standard models. In this eternally evolving plasma cosmos, what lies beyond is not an end or a beginning, but simply an infinite continuation of the same beautiful, filamentary dance of energy and matter that shaped our own corner of existence. The idea of a cosmos that has simply always existed with no dramatic beginning or end brings us to one of the most elegant and historically significant challenges to the Big Bang theory. This is the steady-state theory, a model that captivated the scientific world for decades with its promise of an infinite, unchanging universe. While Einstein's static universe was rendered obsolete by the discovery of expansion, the steady-state model accepted this expansion but proposed a brilliant mechanism to avoid its ultimate conclusion, a finite beginning. Its central tenet was what became known as the perfect cosmological principle. This principle stated that not only does the universe look roughly the same in every direction, the standard cosmological principle, but it also looks the same at all times. The universe on the largest scales is eternal and unchanging in its overall appearance. To maintain this perfect sameness in the face of expansion, the theory's architects Fred Hoyle, Thomas Gould, and Hermann Bondi proposed a radical idea. As galaxies drift apart due to the expansion of space, the density of matter in the universe would naturally decrease, creating an ever-more dilute cosmos. To prevent this, the steady-state theory suggested that new matter is continuously created out of nothing, popping into existence in the void between the receding galaxies. This wasn't a massive, explosive creation event, but a slow, imperceptible trickle, perhaps just a few atoms per cubic kilometer every few billion years. This newly formed matter would then coalesce to form new stars and galaxies, filling the gaps left by the expansion and ensuring that the overall density of the universe remains constant forever. In this view, the cosmos is like an endless river. While individual water molecules the galaxies float away downstream, new water is constantly being added at the source, keeping the river forever full and flowing. There is no need for a beyond because the universe is infinite in both space and time. It is simply more of the same forever. This theory held a powerful philosophical appeal. It portrayed a universe that was immortal and self-renewing, requiring no supernatural creation event. It was a clean, elegant solution that avoided the thorny philosophical problems of a universe springing from a singularity. For a time, it was a serious and respected competitor to the emerging Big Bang model, which Hoyle himself derisively named during a radio broadcast, intending the term to sound absurd. The debate between the two models became one of the great scientific rivalries of the 20th century. It was a classic clash of worldviews, the eternal, steady-state universe versus the evolutionary universe with a definitive beginning. The fate of the steady-state theory, however, was sealed by a discovery made almost by accident. In 1965, astronomers Arno Penzias and Robert Wilson were testing a sensitive microwave antenna and found a persistent, faint hiss of static that came from every direction in the sky, day and night. They tried everything to eliminate it, even cleaning out pigeon nests from the antenna, but the noise remained. This ubiquitous signal turned out to be the cosmic microwave background radiation, the cooled remnant of the incredibly hot and dense early universe predicted by the Big Bang theory. It was the afterglow of the primordial fireball, and its discovery provided overwhelming evidence that the universe was once in a much hotter, denser state. This was something the steady-state theory simply could not explain. In a truly eternal and unchanging universe, there should be no such fossil radiation uniformly bathing the entire sky. The universe would never have been in such a unique hot state. Further evidence against the steady-state model came from observations of quasars, the incredibly bright nuclei of distant galaxies. Astronomers found that these objects only existed at very great distances, meaning we see them as they were billions of years in the past. The fact that they are not found in the nearby, more recent universe indicated that the cosmos was different in the past than it is today. This directly violated the perfect cosmological principle, which demanded that the universe look the same at all times. The universe, it turned out, does have a history. It evolves, it changes. The evidence pointed conclusively to a dynamic cosmos that began in a hot Big Bang, leading to the decline and eventual abandonment of the steady-state theory by the vast majority of cosmologists. Yet the story of the steady-state theory is far from a mere scientific failure. Its importance lies in what it represents, the essential, self-correcting engine of the scientific method. It was a beautiful, logically consistent idea that made testable predictions. When those predictions were contradicted by observational evidence, the theory was modified or, in this case, set aside. This is how science progresses. The rivalry between the steady-state and Big Bang models drove decades of intense research and observational innovation, ultimately leading to a stronger, more evidence-based understanding of our universe. It serves as a powerful reminder that even the most elegant and appealing ideas must bow to the hard facts of reality, and that our quest for knowledge is a process of constant revision and refinement in the face of new discoveries. Yet, for all the grandeur of eternal cycles and vast multiverses, perhaps the most humbling origin story for our cosmos is also the simplest. What if our universe, in all its complexity, began as a random hiccup in the fabric of nothingness itself? This is the astonishing proposition of the universe as a quantum fluctuation. It takes one of the most counterintuitive principles from the world of the very small and scales it up to the ultimate extreme, suggesting that everything we see, from the smallest atom to the largest galaxy cluster, is the result of a cosmic accident that borrowed its existence from the void. To understand this, we need to venture into the bizarre realm of quantum mechanics, where the classical rules of cause and effect break down. In the quantum world, empty space is not truly empty. What we perceive as a perfect vacuum is actually a seething, bubbling foam of activity. Due to the Heisenberg uncertainty principle, which places fundamental limits on what we can know about a particle's energy and position, particles and their antiparticles can spontaneously pop into existence for unimaginably brief moments before annihilating each other and disappearing back into the void. These virtual particles are not just a mathematical curiosity. Their effects have been experimentally verified, such as in the subtle shift of energy levels in atoms, known as the Casimir effect. So, according to our most fundamental theories, nothingness is inherently unstable. It's a restless sea of potential, constantly giving birth to fleeting somethings out of nothing. Now, take this quantum weirdness and apply it not to a single particle, but to the entirety of space-time. The theory proposes that our Big Bang was not a unique event, but simply a quantum fluctuation on a cosmic scale. In an initial state of pure, featureless nothing, a state without space, time, or matter, a random fluctuation could have occurred. Just as a virtual particle pair borrows energy from the vacuum to exist for a fleeting instant, the nascent universe could have borrowed an immense amount of energy to inflate into existence. But here's the critical twist that makes this more than just a one-off event. If the gravitational energy associated with this new universe is negative, it could perfectly balance the positive energy of all the matter and radiation created within it. In this scenario, the total energy of the universe could be zero. Our cosmos would be the ultimate free lunch, a fluctuation that required no net input of energy because all its positive energy is exactly cancelled out by negative gravitational energy. It literally came from nothing, and it owes nothing back. This leads to a profound implication for what lies before or beyond our universe. There is no before in a temporal sense, as time itself began with the fluctuation. What exists beyond the boundaries of our space-time is not a place, but the same primordial, metastable void from which we emerged, and if it happened once, it can happen again. This suggests a different kind of multiverse, not of branching timelines or colliding branes, but of isolated baby universes constantly bubbling up like effervescent foam in a timeless, spaceless void. Each of these universes would be completely disconnected from all the others, each with its own random set of physical laws determined by the nature of its particular fluctuation. We just happen to inhabit one of the rare fluctuations whose laws were conducive to the formation of galaxies, stars, planets, and eventually, life forms capable of pondering their own origins. This idea brings us face to face with one of the oldest and most profound philosophical puzzles of all. Why is there something rather than nothing? The quantum fluctuation theory offers a stark, almost poetic answer. There is something because nothing is unstable. The existence of a universe like ours isn't a statistical miracle begging for a designer. It's an inevitable outcome of the restless nature of reality at its most fundamental level. In an eternal, featureless void, a fluctuation that creates a universe is not just possible. Given enough time, or more accurately, outside of time, it becomes a virtual certainty. The question then shifts from why is there a universe to why are the laws of physics such that a universe can fluctuate into existence? This remains a deep mystery, but it reframes the puzzle in a way that is, for the first time, potentially addressable by science. It suggests that the mystery of existence may be rooted not in a supernatural act, but in the intrinsic properties of quantum fields. After exploring these incredible physical models of cosmic origins, from quantum fluctuations to colliding branes, we arrive at a principle that shifts the entire discussion. It asks not what lies beyond, but why our universe is the way it is in the first place. This is the anthropic principle, a philosophical framework that provides a powerful, if humbling, lens through which to view all the theories we've discussed. It begins with a seemingly obvious statement. We observe the universe to have certain properties because those properties are necessary for us to be here as observers. This simple logic, known as the weak anthropic principle, is almost tautological, but its implications are profound when applied to the cosmos. Consider the fundamental constants of nature. The strength of gravity, the force that binds atomic nuclei, the mass of an electron. These values are not predicted by any current theory. They are, as far as we know, arbitrary numbers that could have been different. Yet, if they were even slightly different, the universe as we know it would be impossible. If the force of gravity were significantly stronger, stars would burn through their fuel in millions of years instead of billions, leaving no time for planets to form and life to evolve. If the strong nuclear force were just a few percent weaker, protons would not be able to bind together, and hydrogen would be the only element in existence. There would be no carbon, no oxygen, no building blocks for life. The universe appears to be exquisitely fine-tuned for our existence. The weak anthropic principle offers a straightforward explanation for this apparent fine-tuning. It's not that the universe was designed for us, it's that we are a product of a universe that happened to have the right conditions. We are simply living in the one niche where the numbers lined up correctly. If they hadn't, we wouldn't be here to notice. This leads to the more controversial strong anthropic principle, which takes this logic a step further. It suggests that the universe must have properties that allow life to arise at some point in its history. This statement feels different. The weak version is a statistical observation. We see what we see because we can. The strong version implies a form of necessity, almost a teleology, as if the cosmos has a built-in bias toward producing consciousness. Proponents of the strong version argue that the presence of observers might be a fundamental constraint on the possible laws of physics, though this veers into philosophical territory that makes many scientists uncomfortable. It raises the question of whether consciousness itself plays a role in shaping reality, an idea that remains firmly in the realm of speculation. However, the true power of the anthropic principle is unleashed when it is combined with the concept of the multiverse. Suddenly, the fine-tuning problem transforms from a mysterious coincidence into an inevitable outcome. If an infinite or near-infinite number of universes exist, each with its own randomly selected set of physical constants, then it is a statistical certainty that a tiny fraction of them will, purely by chance, have the precise combination of numbers necessary for complexity and life. We do not live in a specially created or finely tuned universe. We live in an ordinary one, but one that belongs to the very select group of universes that are capable of hosting observers. What lies beyond our cosmic horizon in this view is not just more space, but a cosmic graveyard of failed universes. Countless realms where gravity was too strong, where nuclear forces were too weak, where the cosmic expansion was too rapid. An unimaginable multitude of stillborn cosmos, dark and barren, where the laws of physics were incompatible with the formation of even a single star. Our universe is the rare, shining exception in a vast desert of hostile realities. This perspective profoundly changes how we interpret our place in the cosmos. It counters the temptation to see our existence as the central purpose of creation. Instead, it suggests we are the beneficiaries of a cosmic lottery with an almost infinite number of losing tickets. This isn't a pessimistic view, but rather a liberating one. It means that the laws of nature we are striving to uncover are not necessarily the only possible laws, nor are they the most elegant or fundamental. They are simply the local bylaws of our particular cosmic neighborhood, the ones that allowed us to come into being. The search for a single, elegant theory of everything might be misguided if our universe is just one possibility in a vast landscape. The anthropic principle doesn't provide the equations for that landscape, but it gives us a crucial reason for why our particular corner of it looks the way it does. It is the ultimate answer to the question of why we find ourselves in such a hospitable universe, not by design, but by the sheer, staggering odds of a multiverse where every possibility is realized. But if the anthropic principle offers a statistical reason for our existence within a cosmic lottery of possibilities, it brings us back to what might be the ultimate logical conclusion of that lottery. We must revisit the mathematical universe hypothesis, the idea we introduced as the Level 4 multiverse, for its implications are so staggering that they demand a deeper exploration. This theory, championed by Max Tegmark, proposes that our physical reality isn't just described by mathematics, it is a mathematical structure. And if that's true, then the ultimate answer to what lies beyond our universe is not more galaxies or different physical constants, but something far more fundamental. The complete set of all mathematical structures, an ensemble of every possible form of existence that logic itself can support. To grasp this, we need to challenge our intuition about what existence really means. We tend to think of the physical world as the primary reality, the rocks, the stars, the atoms that make up our bodies. Mathematics, in this view, is a useful language we invented to describe that reality. The mathematical universe hypothesis turns this completely on its head. It suggests that the mathematical structure is the fundamental reality, and our physical universe is simply a manifestation of one particular, incredibly complex structure. Think of it like the number pi. The digits of pi form an infinite, non-repeating sequence. That sequence and all its properties exist as a mathematical truth, whether or not anyone is calculating it or a universe exists where circles are drawn. Tegmark's radical proposal is that every such consistent mathematical structure has the same claim to physical existence as our own cosmos. there is no difference between the abstract and the concrete. This leads to a multiverse of literally unimaginable diversity, far surpassing the other levels we've discussed. The Level 1 multiverse gave us more stars and galaxies. Level 2 gave us bubble universes with different laws of physics. Level 3 gave us branching timelines, but the Level 4 multiverse contains realities that are not just variations on our theme, they are built on entirely different foundations. Consider the very dimension of time. We experience it as a single, one-way arrow, but what about a universe with two dimensions of time? In such a reality, causality as we know it would break down entirely. An event could have multiple, equally valid pasts, or effects could ripple backward and forward in time in ways that are completely nonsensical to our brains. Life in such a universe is impossible for us to conceive, but if its mathematical structure is consistent, then according to this hypothesis, it exists just as surely as our own. The strangeness goes even deeper when we consider the nature of logic itself. Our universe operates on binary, true or false logic. A statement is either true or it is false. But there are consistent mathematical systems built on fuzzy logic or ternary logic with states of true, false, and indeterminate. A universe governed by such a logic might contain objects that simultaneously exist and do not exist, or events that are both caused and uncaused. Furthermore, some mathematical structures might have no concept of time or space at all. They could be static, eternal landscapes of pure geometric relation, like an infinitely complex frozen crystal. There would be no change, no motion, no history, just a single, timeless mathematical truth. Other structures might be so simple that they contain only a handful of abstract objects and relationships, a minimalist universe with no capacity for complexity or consciousness. What does existence even mean for these alien realities? If a universe has no space, no time, and no matter, in what sense can we say it exists? The mathematical universe hypothesis forces us to divorce existence from perception. Something exists if it is logically consistent. A triangle, by definition, has three sides. That property is true. It exists as a mathematical fact. In the same way, a universe defined by a specific set of equations exists as a mathematical fact. The fact that we, as conscious observers embedded within one particular mathematical structure, require space, time, and matter to exist is simply a property of our local reality, not a requirement for reality itself. We are like characters in a novel who believe the only things that exist are the words on their pages, unaware of the infinite library of other books containing every other possible story. This idea represents a profound and elegant endpoint for the multiverse concept. It dissolves the fine-tuning problem with breathtaking finality. We don't need to ask why our universe's constants are so perfectly tuned for life. In the infinite ensemble of all mathematical structures, only a tiny subset will be complex enough to contain self-aware substructures that can ponder their own existence. We necessarily find ourselves in one of those. It also suggests that the holy grail of physics, a theory of everything that perfectly describes our universe, might be missing the larger picture. The point isn't to find the one correct set of equations, but to understand why we inhabit this particular equation set out of the infinite menu. The mathematical universe hypothesis is the ultimate expression of cosmic democracy, granting full and equal reality to every possible world that logic can dream up, from the wildly complex to the elegantly simple, leaving our own universe as just one particularly interesting entry in the grand catalogue of all that is possible. Now, just when you thought our journey couldn't get any stranger, we arrive at a theory so deeply unsettling that it doesn't just question the nature of the cosmos, but the very validity of your own thoughts and memories. This is the Boltzmann-Brane paradox, a thought experiment that emerges from the cold, hard logic of thermodynamics and probability, and it presents a terrifying possibility for any universe that lasts for an unimaginably long time. It asks a question that is both profound and profoundly disturbing. How can you be certain that the world around you is real and not just a fleeting, elaborate hallucination of a mind that spontaneously popped into existence from the chaos of nothingness? To understand how we get to this bizarre conclusion, we need to start with a fundamental principle of physics, the second law of thermodynamics. This law states that the total entropy or disorder in a closed system always increases over time. The universe, on the whole, is moving from a state of order to a state of disorder. A classic example is a cup of hot coffee left on a table. The heat from the coffee will disperse into the cooler air of the room until everything reaches the same temperature. It's incredibly unlikely for the reverse to happen, for the heat to spontaneously flow back from the air into the cup, reheating the coffee. That would be a massive decrease in entropy, a statistical near impossibility. However, and this is the crucial point, it's not an absolute impossibility. Given enough time, even the most unlikely events can and will occur through random chance. If you waited long enough, the random motion of air molecules could, by sheer fluke, all happen to move in the same direction at once, transferring their energy back into the cup. It would be astronomically rare, but in a truly eternal universe, rare events are inevitable. This is where the physicist Ludwig Boltzmann enters the story in the late 19th century. He was grappling with how our ordered universe could have arisen from chaos, given the second law. His intriguing suggestion was that our entire cosmos might be a rare, giant fluctuation, a low-entropy bubble that randomly formed in a much larger, high-entropy and eternal universe. In an infinite sea of disorder, a pocket of order will eventually appear simply by chance. But here's the twist that Boltzmann himself never considered. If our entire universe is a low-probability fluctuation, then what is more probable? Creating one planet or one galaxy is vastly more likely than creating a whole observable universe with hundreds of billions of galaxies. Creating a single, self-aware human being is more likely than creating the entire evolutionary history of Earth that led to them. And following this logic to its extreme, the most probable fluctuation of all would be the one that requires the least amount of order. Not a whole person, not even a whole body, but just a lone, disembodied brain, complete with all the memories and sensory impressions of a full life, moments before it flickers back out of existence. This hypothetical entity is what we now call a Boltzmann brain. Imagine a single, self-aware mind suddenly coming into being from a random collision of particles in the void. This brain will be equipped with a perfectly fabricated memory of an entire past, our childhood, friends, a career, everything. It would have the vivid sensory experience of reading this sentence right now, of feeling the chair beneath it, of seeing the screen in front of it. From its perspective, its reality would be utterly convincing. But after a few seconds or minutes, the fluctuation would reverse. The delicate, ordered structure of the brain would be instantly smashed apart by the surrounding chaos, and the illusion would vanish. The universe it thought it inhabited would never have existed at all. The paradox arises when we apply this to modern cosmological models, particularly those involving an eternal universe or an eternally inflating multiverse. In such a cosmos that persists for an infinite amount of time, the number of these brief, disembodied Boltzmann brains that will fluctuate into existence should be unimaginably larger, in fact, infinitely larger, than the number of ordinary, evolved brains like ours that exist within a stable, ordered universe. Therefore, if you are a conscious being in an eternal cosmos, the statistics overwhelmingly suggest that you are far more likely to be a momentary Boltzmann brain hallucinating a universe than a real person inhabiting a real 13.8 billion-year-old cosmos. Your belief that you have a past, that the world has a history, that the laws of physics are consistent, would all be a cruel, random accident. This is not proposed as a serious theory about what lies beyond our universe. In fact, most physicists see it as a major problem for the cosmological models that predict it. The Boltzmann-Brane paradox is a reductio ad absurdum, a logical argument that shows if your premises lead to an absurd or unacceptable conclusion, then there must be something wrong with your premises. If a theory like eternal inflation implies that we should all be Boltzmann brains, and we have very good reasons to believe we are not, then that theory might be missing a crucial piece of the puzzle. Perhaps the universe is not eternal in the way we think. Perhaps there is a cosmic boundary condition that prevents such fluctuations, or a law of physics we haven't yet discovered that makes evolved observers fundamentally more probable than fluctuated ones. The paradox forces cosmologists to refine their models, to search for those that naturally avoid this bizarre and unsettling outcome. It serves as a profound reminder that when we push our understanding of reality to its absolute limits, we can encounter puzzles that challenge not just our science, but the very foundations of our conscious experience. From the unsettling paradox of a universe that might be populated by fleeting, disembodied minds, we now turn to a concept that is equally astounding but far more tangible, at least in the equations of physics. This is the idea of the white hole, the theoretical opposite of a black hole. We are all familiar with a black hole's defining feature. Its immense gravitational pull creates an event horizon, a point of no return from which nothing, not even light, can escape. A white hole, by contrast, would have an event horizon from which nothing can enter. It is a cosmic gusher, a one-way door in the fabric of space-time that only expels matter and energy, forever pushing everything away. If a black hole is the universe's ultimate drain, a white hole would be its fountainhead, a region of space that is utterly unreachable and eternally erupting. The concept of a white hole emerges quite naturally from the same mathematics that describe black holes. When Karl Schwarzschild found the first solution to Einstein's equations of general relativity for a non-rotating spherical mass, the resulting geometry contained a surprise. It described not one, but two singularities points where the equations break down and density becomes infinite. One was the black hole singularity we know, hidden behind its event horizon. The other was a white hole singularity, which theoretically exists in the past of the object. This isn't just a mathematical curiosity. It suggests that if you could reverse the direction of time in the equations for a black hole, its behavior would perfectly describe a white hole. A black hole absorbing matter over billions of years would, in reverse, be a white hole spewing that same matter out over billions of years. The symmetry is elegant, but the challenge has always been whether such an object could actually form and persist in our forward arrow of time universe. This leads to one of the most breathtaking applications of the white hole hypothesis, an explanation for the Big Bang itself. Could the origin of our entire cosmos have been a white hole event? Imagine the scenario. In a parent universe, a massive star collapses, forming a black hole. From the perspective of an outside observer in that universe, matter and light vanish behind the event horizon, lost forever. But what is the ultimate fate of that matter inside the black hole? Some solutions to the equations of general relativity, particularly for rotating black holes, suggest that the crushing singularity might not be a final destination, but a bridge, a wormhole, connecting to another region of spacetime. This other end of the wormhole would not be an entrance but an exit, and the violent, explosive beginning of that new spacetime continuum would look from the inside exactly like a Big Bang. In this view, our universe did not erupt from a mysterious point of infinite density in a pre-existing void. Instead, it was born from the interior of a black hole in another, grander cosmos. We are not on the outside of a white hole looking in. We are on the inside, living in the expanding aftermath of that primordial eruption. This theory beautifully ties together several of the ideas we have explored. It connects directly to the black hole cosmology theory, suggesting a mechanism for that infinite nesting of universes. It also provides a potential resolution to the mystery of what happened before the Big Bang. There was no before in our timeline, but there was a elsewhere, the parent universe where the stellar collapse that seeded our existence took place. What lies beyond the ultimate edge of our expanding universe is not empty space, but the interior of that progenitor black hole, a realm with its own laws of physics and flow of time that we can never access. Our entire cosmic history is the unfolding of a white hole event, a reality that began as an exit from another. Despite its mathematical elegance and conceptual appeal, the white hole hypothesis faces a significant physical problem: stability. The second law of thermodynamics, which governs the increase of disorder, seems to be fundamentally opposed to the existence of a white hole. Think of it this way: a white hole would be a region of extremely low entropy, a perfectly organized source spewing out energy. But the universe tends toward disorder. If you were to try and create a white hole, perhaps by somehow reversing the collapse of a star, it would be fantastically unstable. Any single particle of dust or wisp of radiation straying near its event horizon would be enough to collapse the entire structure, causing it to immediately transform into a black hole. It's like trying to balance a pencil perfectly on its point. The slightest disturbance sends it tumbling into a far more stable state. For this reason, most physicists consider white holes to be highly improbable long-term features of our universe, beautiful mathematical phantoms that are unlikely to exist in reality. However, some speculative theories offer a way out. Perhaps white holes are not objects that form from ordinary matter, but are instead primordial relics from the extreme conditions of the Big Bang itself, frozen in time and persisting to this day. Or, in a more modern twist rooted in quantum gravity, what if the final stage of a black hole's evaporation via Hawking radiation is not its disappearance but its transformation? After a black hole has radiated away nearly all of its mass, some theories suggest the quantum gravitational effects at its core could become so dominant that the black hole effectively becomes a white hole, explosively releasing its remaining energy in a final burst. These fleeting quantum white holes would be too small and short-lived to birth new universes, but they hint that the boundary between cosmic absorption and cosmic expulsion might not be as absolute as classical physics suggests. While the brilliant white portal pouring a new universe into the void remains in the realm of theoretical possibility, it stands as a powerful testament to the profound connections general relativity reveals between the very large, the very small, and the very beginning of everything. If the universe is a hologram or a simulation, then what is the actual substance from which this grand illusion is woven? A growing number of physicists and philosophers are converging on a startling answer: information. Not matter, not energy, but bits, the fundamental units of data, may be the true bedrock of reality. This idea, often called the it from bit doctrine, suggests that every particle, every force field, and even the fabric of spacetime itself might be a manifestation of information processing. What we perceive as the solid, tangible world could be the output of a cosmic computation, and what lies beyond our universe might be the processor running the code. The seeds of this radical perspective were planted by the legendary physicist John Archibald Wheeler. In the later part of his career, Wheeler became fascinated by the deep interplay between quantum mechanics and observation. He famously conducted thought experiments like the delayed choice experiment, which showed that the past history of a particle isn't fixed until it is measured in the present. This led him to a profound conclusion: that reality is fundamentally participatory. The universe is brought into being by the act of observation. He encapsulated this idea in the phrase, it from bit. It refers to every particle, every field of force, even the spacetime continuum itself, all the tangible things of the physical world. Bit signifies a binary choice, a yes or no answer to a question. Wheeler proposed that every aspect of the physical world, ultimately derives its existence from binary decisions made in response to questions posed by observers. In this view, the universe is not a collection of objects, but a network of information exchanges. The cosmos is built not of stuff, but of answers. This perspective finds powerful support in our most advanced theories of physics. The holographic principle, as we discussed, suggests that all the information describing a three-dimensional volume of space is encoded on its two-dimensional boundary. This is a fundamentally informational description of reality. The information content is what's primary. The three-dimensional world is a derived phenomenon. Similarly, black hole thermodynamics tells us that the maximum amount of information you can store in any region is proportional to its surface area, not its volume. This is like saying the information capacity of a hard drive is determined by the area of its platters, not the thickness of the drive itself. These discoveries point to a universe that operates like a colossal information processing system. The laws of physics, then, are not laws about things, but the algorithms that govern how this information is transformed and updated. Gravity, electromagnetism, and the nuclear forces might be emergent properties of an underlying computational process. This idea, known as digital physics or pancomputationalism, takes the it-from-bit concept to its logical extreme. It proposes that the universe is a computer and the unfolding of events over time is a computation. In this view, the passage of time is akin to the ticking of a cosmic clock cycle. At each Planck time, the smallest possible unit of time, the universe updates its state based on a set of fundamental rules, much like a cellular automaton where the state of each cell in a grid is updated based on the states of its neighbors. The seemingly smooth, continuous motion we see in everyday life would be an illusion, much like the smooth motion in a movie is created by a rapid succession of still frames. At the most fundamental level, reality is pixelated both in space and time, running on a substrate of pure information. So, if the universe is a computation, it naturally leads us to wonder about the nature of the computer. What lies beyond our cosmic horizon in this informational perspective? The possibilities are as fascinating as they are strange. One possibility is that our universe is a simulation running on a hyper-advanced computer in a base reality, as the simulation hypothesis suggests. In this case, what's beyond is the physical hardware of that computer, the servers, the memory, the processing units existing in a parent universe with its own, perhaps very different physical laws. The programmer of this simulation might be an advanced civilization, or it could be an automated process for generating universes. Another, even more mind-bending possibility is that there is no beyond in the traditional sense. The universe might not be running on an external computer at all, but could be a self-contained mathematical structure that just is a computation. This connects back to the mathematical universe hypothesis. In this view, the universe is not being computed by something else. Its existence is synonymous with the execution of its own mathematical rules. The hardware is the mathematical structure itself. There is no deeper reality because the information and the computation are the fundamental reality. Asking what runs the code is like asking what holds up the turtle that holds up the world in the old myth. It's a question that might not apply if the universe is ultimately mathematical and informational in nature. This informational view of reality provides a unifying framework that ties together many of the theories we've explored. The holographic principle, the simulation hypothesis, and even the quantum multiverse can all be seen as different perspectives on a cosmos whose essence is information. It transforms our quest for a theory of everything from a search for the ultimate particle or force field into a search for the ultimate algorithm, the foundational code from which all of physical reality is compiled. While this might feel like an abstract and disorienting concept, it also offers a new kind of elegance. It suggests that at the heart of the cosmos' magnificent complexity lies a beautiful and perhaps even knowable simplicity. The universe may not be a machine made of cogs and gears, but a sublime and ongoing calculation whose output is everything we have ever known. Now, we shift our focus from the cosmic scale to the very fabric of matter itself, to a theory that seeks to complete the picture of our universe from the ground up. This is the idea of supersymmetry, often abbreviated as SUSY. While it might sound like an abstract concept from particle physics, its implications for the nature of reality are so profound that it paints a radically different picture of what our cosmos might truly be. Supersymmetry isn't directly about what lies beyond our cosmic horizon in space, but rather it's about what lies beyond our current, incomplete understanding of the fundamental laws. It proposes that the reality we perceive is a broken, asymmetric fragment of a far more elegant and complete whole. To understand why this is such a compelling idea, we first need to look at our current blueprint for the universe, the standard model of particle physics. This model is one of the greatest achievements of human intellect, a precise catalogue of the fundamental building blocks of matter and the forces that govern their interactions. It includes particles like electrons and quarks, which make up the atoms in our bodies, and force carriers like photons, which mediate light and electromagnetism. The standard model has been tested with incredible precision and has passed every experimental challenge thrown at it. But for all its success, physicists know it's an incomplete picture. It's like having a beautiful, intricate map that perfectly describes a single continent, while knowing full well that an entire world remains to be discovered beyond its edges. The standard model has some glaring gaps. For one, it offers no candidate for the mysterious dark matter that makes up about 85% of the matter in the universe. It also fails to incorporate gravity, the most familiar force in our daily lives, into its quantum framework. Furthermore, the model requires seemingly arbitrary and fine-tuned parameters to work, like the specific masses of particles, which feel like inputs rather than natural outcomes of a deeper theory. Supersymmetry emerges as an elegant solution to many of these problems. At its heart, it's a profound kind of symmetry. In physics, symmetries are incredibly powerful. They are transformations that leave the laws of nature unchanged. For example, the laws of physics are the same in all directions. That's a rotational symmetry. Supersymmetry proposes a new, deeper symmetry, a relationship between the two fundamental classes of particles in the universe. All particles are divided into two distinct families. First, there are fermions like electrons and quarks. These are the particles that make up matter. They are the stubborn individualists of the quantum world, obeying the Pauli exclusion principle, which prevents them from occupying the same quantum state. This is why solid matter exists. It's why you don't simply fall through the floor, because the electrons in your atoms are repelled by the electrons in the floor's atoms. The second family are bosons, like photons and gluons. These are the force carriers, the social butterflies that mediate the interactions between matter particles. Bosons are happy to pile on top of each other, which is how we get coherent phenomena like laser beams. What supersymmetry proposes is that for every known fermion, there should be a superpartner boson, and for every known boson, a superpartner fermion. This would create a beautiful, balanced partnership between matter and force. The electron, a fermion, would have a superpartner called the selectron, a boson. The photon, a boson, would have a superpartner called the photino, a fermion. If this symmetry were perfect and unbroken in our everyday world, these superpartners would have the same mass as their standard counterparts. We would see selectrons and photinos everywhere, but we don't. This is where the concept of broken symmetry becomes crucial. Think of it like a perfectly sharp pencil balanced on its tip. That state has a high degree of symmetry. It looks the same from every horizontal direction, but it's incredibly unstable. The slightest disturbance will cause it to fall, breaking that symmetry and landing in one specific random direction. The universe, according to SUSY, may have been in a state of perfect supersymmetry at its birth, an era of unimaginable energy and temperature. But as the cosmos expanded and cooled, this perfect symmetry was broken. The superpartner particles acquired huge masses, becoming so heavy that they faded from view in our current, low-energy universe. We are living in the aftermath of that cosmic fall, only able to perceive the light, standard particles, while their heavy superpartners remain hidden. The implications of this are staggering. If correct, it means that every single particle we know and love has a hidden, heavier twin. Our reality is just one half of a much larger, more symmetric reality. What lies beyond our perceived reality is not a different place, but a more complete state of being, a higher level of symmetry that we only see a broken reflection of. This has direct, testable consequences. The lightest of these hypothetical superpartners is a prime candidate for dark matter. This particle, often called the neutralino, would be stable, electrically neutral, and would only interact very weakly with ordinary matter, exactly the properties required for the invisible stuff that holds galaxies together. Furthermore, supersymmetry provides an elegant mechanism for unifying the fundamental forces. At the extremely high energies where supersymmetry is restored, the strengths of the electromagnetic, weak, and strong nuclear forces are predicted to converge to a single value, suggesting they are all manifestations of one primordial superforce. The hunt for these superpartner particles has been one of the great quests of modern physics, driving the design of massive experiments like the Large Hadron Collider. While no direct evidence for supersymmetry has been found yet, the theory remains a cornerstone of many attempts to build a more complete theory of everything, such as string theory, which requires supersymmetry for its mathematical consistency. It represents a profound hope that beneath the seemingly messy and arbitrary constants of our world lies an architecture of breathtaking beauty and simplicity, a symmetric universe waiting to be discovered just beyond the edge of our current perception. We have journeyed through theories that propose our universe is one of many in a vast multiverse, that it might be a holographic projection or even a sophisticated simulation. But one of the most elegant and intellectually satisfying proposals comes from the collaboration of two towering figures in theoretical physics, Stephen Hawking and James Hartle. Their idea, known as the no-boundary proposal, tackles the most persistent and perhaps misguided question of all. What happened before the Big Bang? Hawking and Hartle's revolutionary answer is that the question itself is based on a flawed assumption about the nature of time. There was no before because the universe has no beginning in time, just as the Earth has no edge in space. To grasp this, we need to let go of our everyday intuition about time as a straight line that stretches infinitely into the past and future. We naturally picture the Big Bang as a single point on that line, a moment of creation, and we instinctively wonder about the empty stretch of time that must have existed prior to it. The no-boundary proposal suggests this image is wrong. Instead, Hawking and Hartle applied the principles of quantum mechanics, the rules that govern the probabilistic, fuzzy world of the very small, to the universe as a whole. In quantum theory, particles don't have perfectly defined paths. Instead, they explore all possible paths simultaneously. Hawking and Hartle proposed that the universe itself behaves in a similar way. When we go back in time toward the Big Bang, the nature of time itself changes. It becomes more like a dimension of space. This is where their famous analogy of the Earth becomes essential. Think about the North Pole. What lies north of the North Pole? The question is meaningless. The North Pole is a boundary, not in the sense of a cliff you can fall off, but as a point where the definition of north ceases to have any meaning. You can travel north until you reach the pole, but once you're there, every direction you take is south. The Earth's surface is finite. You can traverse it, but it has no edge or boundary. It is a closed, self-contained surface. Hawking and Hartle proposed that the universe, in its entirety, is like this, but in 4 dimensions, 3 of space and 1 of time, woven together into a 4-dimensional shape. In this view, the Big Bang is not an explosion in a pre-existing void, but is analogous to the North Pole. It is a point in the history of the cosmos where the concept of before simply evaporates, just as north vanishes at the pole. Imagine the timeline of the universe not as a straight line, but as a curve that loops back on itself. At the far left of our mental diagram, where we would normally place the Big Bang singularity, the line doesn't just start abruptly. Instead, it smoothly rounds off like the bottom of a curved, bowl-shaped surface. In this picture, there is no sharp, singular beginning where the laws of physics break down. Instead, the universe has a gracefully rounded, closed geometry in the past. Asking what came before the Big Bang is like asking what is south of the South Pole. The question presumes a linear continuation that doesn't exist in this closed geometry. The universe is simply complete, entire unto itself, with no need for an external cause or a mysterious starting gun. It just is. What does this mean for the origin of everything? In the no-boundary proposal, the universe spontaneously creates itself out of nothing, not in a dramatic flash, but through a smooth, quantum mechanical process. There is no boundary in space or time that requires some external agent to set the initial conditions. The laws of physics hold everywhere, even at the universe's inception. This provides an incredibly elegant solution to the problem of what caused the Big Bang. It eliminates the need for a cause altogether by removing the singular beginning that demanded one. The cosmos, in this view, is a self-contained, finite but unbounded entity. It has a specific, finite size in spacetime, but it has no edges or boundaries, making the question of what lies beyond its beginning as nonsensical as asking what lies beyond the surface of a sphere. This proposal offers a profound sense of closure and completeness, painting a picture of a cosmos that is not only mathematically consistent but also philosophically serene, a universe that is its own origin and its own destiny. After exploring the universe as a computation, we now turn to a theory that re-enchants the cosmos, proposing that the most mysterious aspect of existence, consciousness, is not a rare accident of biology but a fundamental feature of reality itself. This is panpsychism, an ancient idea experiencing a modern resurgence, which suggests that mind and matter are not separate substances but two sides of the same cosmic coin. The term comes from the Greek pan, meaning all, and psyche, meaning soul or mind. It is the proposition that some form of consciousness, or at least the raw ingredients for it, is present in everything. From the swirling electrons in an atom to the vast galaxy clusters, every piece of the universe possesses an inner life, however simple or alien it might be. In this view, what lies beyond the physical structure of our universe might not be more space or other dimensions, but a profound, all-pervading consciousness of which our own awareness is merely a tiny fragment. This idea gains traction when we confront what philosophers call the hard problem of consciousness. The easy problems involve understanding the mechanics of the brain, how we process information, focus our attention, or discriminate between stimuli. These are challenges that neuroscience is steadily unraveling. The hard problem articulated by philosopher David Chalmers is the problem of experience itself. Why should all that neural processing be accompanied by a subjective inner life? Why does the firing of certain neurons in your brain feel like the rich, red experience of a sunset or the sharp sting of pain? We can describe the physical processes of light hitting a retina and signals traveling to the visual cortex in perfect detail. But nowhere in that chain of events do we find an explanation for the qualitative feeling of seeing. This gap between objective physical description and subjective experience is the central mystery. Materialism, the dominant view that only physical matter is real, seems to hit a wall here. How can you get something as immaterial as experience from something that is entirely material? Panpsychism offers a radical yet elegant solution. It posits that consciousness is not something that emerges from complex arrangements of unconscious matter. Instead, consciousness is a fundamental property as basic as mass, charge, or spin. Just as electrons have a negative charge by their very nature, they might also possess a tiny spark of proto-consciousness. This isn't to say an electron is thinking or feeling emotions. Its inner life would be unimaginably simple, perhaps just a bare whisper of experience. But when these simple conscious entities combine in increasingly complex ways, forming atoms, molecules, neurons, and brains, their individual sparks of consciousness can combine and unify, giving rise to the rich, complex stream of awareness that you and I experience. In this view, your mind isn't a ghost in the machine. It is the conscious interior of the complex physical system that is your brain, just as the wetness of water is a property that emerges from the collective behavior of H2O molecules. This perspective completely reframes our place in the cosmos. We are not conscious beings living in an unconscious universe. We are the universe becoming conscious of itself. Our thoughts, feelings, and sensations are not isolated events inside our skulls. They are localized expressions of a cosmic property. This provides a profound sense of connection to everything around us. The tree outside your window, the rock on the ground, the distant star, each has its own, perhaps unfathomable, interior perspective. Modern proponents of panpsychism, like philosopher Philip Goff, argue that this view is actually more scientifically parsimonious than traditional materialism. It doesn't require us to believe that consciousness magically pops into existence at some arbitrary threshold of brain complexity. Instead, it integrates consciousness seamlessly into our scientific worldview as a fundamental feature that has always been there. The laws of physics that govern the behavior of matter would be incomplete without also accounting for this intrinsic mental aspect. The implications for what lies beyond are staggering. If consciousness is truly fundamental, then the universe itself could be seen as a single, vast conscious entity. Our individual minds might be like neurons in a cosmic brain, each contributing to a grander awareness that we cannot possibly comprehend. This idea, known as cosmopsychism, suggests that the ultimate reality is mental. The physical universe we observe, the galaxies, the laws of physics, is the external appearance of this cosmic mind. This doesn't necessarily imply a traditional, personal God, but rather an immense, perhaps timeless, field of consciousness within which all lesser conscious entities participate. It offers a vision of a universe that is not cold and mechanical, but alive, awake, and deeply interconnected. While this theory may lie at the farthest reaches of scientific speculation, it challenges us to consider that the greatest mystery of all might not be out there in the distant void, but is the very nature of the awareness with which we are exploring it. But if the no-boundary proposal offers a serene, self-contained universe with no beginning and no end, our next theory presents a future that is anything but serene. This is the scenario of the Big Rip, a cataclysmic finale driven by a particularly vicious form of the very force that seems to be dominating our cosmos today, dark energy. To understand this terrifying possibility, we need to take a closer look at the mysterious entity that's pushing our universe apart. We've known since the late 1990s that the expansion of the universe is accelerating, but the exact nature of the dark energy causing this acceleration is still one of cosmology's greatest mysteries. Its behavior is described by a number called its equation of state, represented by the letter W. This number is essentially a measure of the pressure that dark energy exerts. For the expansion to be accelerating at a constant rate, as many models suggest, this W would need to be exactly -1. This is the simplest scenario, often associated with Einstein's cosmological constant, leading to a universe that expands forever towards a cold, quiet heat death. But what if dark energy is something more exotic? What if its W is less than -1? This is where we enter the realm of phantom dark energy. A substance with this property wouldn't just maintain a constant repulsive force. Its repulsive force would actually grow stronger over time. Think of it not as a steady push, but as a pedal being pressed ever harder to the cosmic floor. The energy density of this phantom field wouldn't dilute as the universe expands, it would increase. This sets the stage for a finale of unimaginable violence. The timeline of the Big Rip is as methodical as it is horrifying. It wouldn't happen all at once. First, the accelerating expansion would become so fierce that it would overcome the gravitational glue holding together the largest structures in the universe. Galaxy clusters, those immense cities of stars, would be the first to be pulled apart. Their member galaxies would be flung away from each other into the ever-widening emptiness. But the phantom energy's grip would only tighten. Next, the gravitational bonds within individual galaxies would fail. The Milky Way would be shredded, its stars scattered like dust in a hurricane, each one sailing off into its own lonely trajectory through the void. As the repulsive force continues to intensify, it would eventually become stronger than the forces holding individual solar systems together. A few tens of millions of years before the end, the phantom energy would be powerful enough to tear planets from their stars. The Earth would be ripped away from the Sun, an orphaned world hurtling into the darkness, but the destruction would not stop there. In the final moments, the phantom energy's strength would surpass even the nuclear forces that bind matter itself. About half an hour before the end, the expansion of space within our solar system would be so violent that it would tear the Sun and the Earth apart into their constituent atoms. And in the last unimaginable fraction of a second, the fabric of spacetime itself would be subjected to forces greater than those that hold atomic nuclei together. Protons and neutrons would be shredded. Quarks would be pulled apart from one another. Every molecule, every atom, every fundamental particle would be separated from every other by an infinite distance, moving faster than the speed of light relative to one another. In this ultimate extrapolation, the phantom energy would become infinitely powerful, ripping apart the very continuum of space-time. The universe would cease to be a cohesive entity. It would become a collection of isolated particles that can never interact again, forever lost in an absolute and featureless void. This leads us to the starkest answer yet to our central question: what lies beyond this cataclysmic end? The answer is a true and absolute nothingness, not empty space because space itself would have been torn asunder. Not the vacuum of quantum fluctuations, because the concept of a where or a when for those fluctuations to happen would have ceased to exist. The Big Rip doesn't just lead to a dead universe, it leads to the dissolution of the stage upon which the universe plays out. It is the ultimate erasure, a finale with no encore, not even silence, because silence requires a medium through which sound could, in principle, travel. What remains is a state beyond physics, a void so complete that the words we use to describe it fail. It is a beyond that is, by definition, unreachable and unknowable, because any instrument or consciousness that could perceive it would have been annihilated in the process. While this scenario sounds like the plot of a cosmic horror story, it is important to stress that it is a serious, albeit speculative, possibility grounded in our current measurements. The value of W for dark energy is incredibly difficult to pin down with precision. Some observational data, while still within margins of error, have occasionally hinted at values slightly less than -1, leaving the door open for the phantom energy hypothesis. The Big Rip serves as a powerful reminder that the fate of the cosmos is not yet written. The same dark energy that illuminates the distant fate of the universe also holds within it the potential for its ultimate destruction. It presents a cosmic deadline, a timer counting down to an end where the very concepts of before and after lose all meaning, leaving us with a profound and haunting vision of finality. Returning to the canvas of the brane multiverse, we find a theory that injects a specific, spectacular drama into the birth of our cosmos. We've already pictured our universe as a three-dimensional membrane, or brane, floating within a higher dimensional space called the bulk. But what if this grand cosmic arena is not a serene, placid sea, but a dynamic and sometimes violent collision zone? This brings us to the ekpyrotic universe scenario, a theory that proposes our Big Bang was not a mysterious eruption from a singularity, but the cosmic equivalent of a car crash, a colossal impact between our brane and a neighboring one. Imagine two gigantic, perfectly flat sheets, like immense slices of a cosmic loaf of bread, drifting parallel to each other in an unseen, higher-dimensional void. These are branes, and they are separated by a tiny distance in an extra compactified dimension. According to this model, these branes are not static. They are drawn toward each other by a force acting across the bulk. They approach, oscillate, and eventually collide. The energy released in this monumental impact is almost beyond comprehension. From the perspective of any beings confined to one of these branes, this collision would manifest as an unimaginable flash of heat and light, a sudden, universe-filling fireball from which all matter and energy erupts. This, the theory suggests, is what we call the Big Bang. Our entire cosmic history is the aftermath of that singular, violent encounter. This vision completely reimagines the beginning of everything. Instead of a singularity where the laws of physics break down, the ekpyrotic model offers a more well-behaved genesis. The slow, gentle approach of the branes before the collision has a natural smoothing effect, stretching and flattening any wrinkles or irregularities. This elegantly explains why our observable universe is so remarkably uniform in all directions, a long-standing puzzle in standard Big Bang cosmology. The Big Bang wasn't a beginning from nothing. It was a transition, a phase change triggered by an external event in a larger, meta-universal reality. What lies before our universe, then, is not a temporal void, but the history of our brane and its cosmic neighbor, their approach through the bulk setting the stage for the creation we inhabit. This framework also suggests a cyclical view of cosmic history. After the collision, the two branes don't annihilate each other. They rebound, propelled apart by the force of the impact, and begin the long expansion that defines our current universe. But the attractive force between them remains. Over an almost inconceivable timescale, the branes will slow their outward flight, stop, and begin to approach each other once more. This sets the stage for another collision, another Big Bang, and the birth of a new universe from the ashes of the old. In this eternal cycle, our cosmos is just one episode in an infinite series of cosmic deaths and rebirths. What lies beyond the ultimate fate of our universe is not an empty heat death, but the inevitable approach of our celestial sibling, destined to meet us again and ignite the next great cycle of creation. This makes the multiverse an intensely active and dynamic place. What lies beyond our brane is not a static collection of other universes, but a realm of constant motion and potential interaction. Other branes could be on trajectories that will one day bring them into contact with ours, potentially causing future cosmic catastrophes or new beginnings. Our cosmic home is not an isolated island. It is a participant in a grand, rhythmic ballet across the dimensions. But could such a fantastical event leave any tangible evidence? Incredibly, physicists have proposed a way we might find a scar from this primordial accident. The thinking goes that if our brane collided with another, the impact might not have been perfectly uniform. There could have been slight variations in the energy or angle of the collision. These imperfections would have imprinted themselves as subtle irregularities in the earliest moments of our universe. As the universe expanded and cooled, these imprints would have been frozen into the oldest light we can observe, the cosmic microwave background radiation, the afterglow of the Big Bang itself. Researchers have searched for specific patterns in this background glow, such as concentric circles of temperature variation that could act like cosmic bruises, evidence of a collision with another brane in the distant past. While such evidence remains elusive and controversial, the very fact that we can conceive of a test for an event that occurred in a higher dimensional space is a testament to the power and creativity of modern theoretical physics. And so we arrive at our final destination on this incredible journey, not at an answer, but at the edge of a profound and humbling realization. After exploring 24 theories that stretch the imagination, from multiverses to simulations, from cosmic cycles to holographic projections, we must confront Theory 25, which is perhaps the most important of all. It is the possibility that the ultimate nature of what lies beyond our universe is something we, as human beings, are fundamentally incapable of comprehending. Our entire quest has been built upon the tools of human logic and mathematics. But what if the true reality operates on principles that lie entirely outside the framework of our perception and reasoning? Consider the world from the perspective of a goldfish swimming in its bowl. Its reality is defined by the curved glass, the water temperature, the flakes of food that fall from above. It has no framework for understanding the internet, global finance, or the principles of semiconductor physics that power the smartphone a person might be using while watching it. The concepts are not just complex, they are categorically outside the goldfish's domain of experience. Its brain is not wired to process them. In a very similar way, our human brains evolved to navigate a world of medium-sized objects moving at moderate speeds, a world governed by survival, social dynamics, and the predictable rhythms of a planet orbiting a star. We have brilliantly extended our senses with telescopes and particle accelerators, but we may have hit a hard limit. The fundamental laws governing the meta-reality beyond our cosmic horizon could be as alien to us as a smartphone is to a goldfish. This isn't a failure of science, it's a recognition of its boundaries. Every theory we've discussed, no matter how wild, is ultimately a product of the human mind. The Level 4 multiverse of mathematical structures is the absolute frontier of this approach, suggesting that anything logically consistent must exist. But what if the true nature of existence includes phenomena that are logically inconsistent or operate on a pre-logical foundation? We have no mental faculties to even approach such a concept. Our mathematics, for all its power, is a language we invented to describe the patterns we observe. It is not necessarily the native language of the cosmos at its most fundamental level. There might be deeper truths that mathematics simply cannot capture, realities where 1 + 1 does not equal 2, where cause and effect are not sequential, or where the very idea of an object or a law is meaningless. This brings our exploration full circle back to the sense of wonder we began with. Gazing up at the night sky, we are confronted with a mystery that may be permanently beyond our grasp. And there is a strange beauty in that. The unknown is not just a temporary gap in our knowledge to be filled. It might be an eternal companion, a fundamental feature of our existence in this particular universe. Embracing this mystery does not mean giving up on the quest for knowledge. On the contrary, it makes the quest all the more noble. We are finite beings daring to ask infinite questions, pushing against the very limits of what it means to be human. The value lies not in finding a final answer, but in the act of asking, in the courage to look into the abyss and let our imagination soar. So, as we conclude this tour of cosmic possibilities, remember that each theory is a testament to human curiosity and creativity. They are not necessarily competing truths, but different lenses through which we attempt to glimpse the unglimpsable. The true takeaway is not a checklist of 25 ideas, but a renewed sense of awe for the grandeur of the cosmos and our small but spirited place within it. The greatest discovery may be the understanding that some doors are meant to remain closed, not because we are not worthy, but because the room beyond is built in dimensions our minds cannot enter. And in that realization, we find a deep and profound peace, accepting the magnificent mystery of it all. And so, we've reached the end of our journey, having ventured through 25 incredible windows into the ultimate unknown. From the endless repetitions of the Level 1 multiverse to the cosmic hologram, from the cyclical rebirths of the ekpyrotic universe to the startling possibility that we might be living in a simulation, we have explored the very frontier of what human curiosity can conceive. Each theory, in its own way, is a masterpiece of imagination and logic, a testament to our relentless drive to understand our place in the grand scheme of things. We've seen how the universe might be one of countless bubbles in an eternally inflating sea, how reality might constantly branch with every quantum choice, and how our entire cosmic history could be the aftermath of a collision between dimensional membranes in a higher dimensional reality. What becomes undeniably clear after this tour of cosmic possibilities is that the true answer may forever lie beyond our grasp. The fundamental nature of what, if anything, lies beyond the cosmic horizon might be something our human brains, evolved for survival on an African savanna, are simply not equipped to comprehend. But here's the beautiful part: that's perfectly okay. The value of this exploration isn't found in a final, definitive answer. It's found in the asking itself. The act of peering into the abyss and daring to propose an answer, no matter how wild, is what fuels the engine of science and philosophy. It is this profound sense of mystery that pushes us to build bigger telescopes, more powerful particle colliders, and more elegant equations, all in the hope of catching a fleeting glimpse of a truth larger than ourselves. This question, what lies beyond our universe, remains one of the most profound we can ever ask. It touches on everything we are: our curiosity, our courage, and our deep-seated need to find meaning in the vast, silent cosmos. So now, we want to hear from you. The conversation doesn't end here, it's just beginning. Which of these 25 theories captured your imagination the most? Was it the elegant democracy of the mathematical universe, or the terrifying finality of the Big Rip? Or do you have your own wild, speculative idea that we didn't even cover? Maybe you think the universe is a single giant atom in an even larger being, or perhaps all of existence is the dream of a cosmic entity. Let your imagination run free in the comments below. We genuinely want to know what you think. If this journey to the edge of reality sparked your curiosity, then you won't want to miss what's next. Our channel is dedicated to exploring the biggest mysteries of the cosmos, from the nature of black holes to the search for alien life. Make sure to hit the like button if you enjoyed this video, and subscribe to the channel so you never miss an adventure into the unknown. Thank you for joining us on this incredible expedition to the very limits of existence. Keep wondering, keep questioning, and we'll see you in the next video.